Let's look at a new conic today. Here's our equation of our new conic. X squared over a squared minus y squared over b squared equals 1. That looks vaguely familiar, except there's a subtraction sign rather than an addition sign. It says to solve for y. So let's go ahead and solve for y. How are we going to do that? Well, let's move the y squared over. So we'll have y squared over b squared is equal to, and let's move the 1 over as well. So we'll have x squared over a squared minus 1. And then to get our fractions together, we're going to get common denominators. So equals x squared minus a squared all over a squared, right? Because a is really, 1 is really a squared over a squared. Okay. And then from there, we'll move the b over. So we'll have y squared is equal to, and then so what we have is b squared times, and what I'll do is actually move this a squared with it, b squared over a squared, times, and then x squared minus a squared. All right, well, I guess there's only one thing left to do, which is get rid of this square, and we do that by square rooting both sides. Don't forget, square root needs plus minus. So we have y is equal to plus minus. Now the square root of a b squared is just going to be b. The square root of a squared is just going to be a. You can do that with your properties of square roots and fractions. And then you can separate these into two parts, right? The square root of m times n is equal to the square root of m times the square root of n. So we're just now going to have the square root of x squared minus a squared contained within the root as well. So there we go. We have our y equals equation. Let's take a look at that equation. As the absolute value of x gets very large, how does this affect the y value? So let's rewrite our equation. Y is equal to plus minus b over a square root x squared minus a squared. So x is getting very, very large. This number here is getting bigger and bigger and bigger. How does it affect y? Well, if we remember what that equation looked like from the very beginning, keep in mind a and b are really just numbers. They're static numbers. They're constant. They hold in place. So imagine, let's say a was even like a 25, right? And a squared is like a 25. If x is getting larger, like 100, 1,000, 1,000,000, 10 million, whatever it is, what you'll notice is that the a squared is really getting less and less significant. It's basically getting insignificant. So this is basically almost like approaching that value of 0. It really makes no difference at all, because this x value is getting so large. Now, what is the square root of x squared, though? No matter what that x value is, you know that square root and square just cancel each other out. So as this x value gets larger and larger, you're actually approaching the value of y equals plus minus b over a times x. Oh, that's just a line. B over a is just some kind of slope for the value of x. Okay, so, but however, remember that technically this really wasn't 0. The a squared technically is there. So this is just approaching this line here. We are approaching, but we will never touch. But never touch this line. Wait, I think we have a name for that. Do you remember that name? Hopefully, in your head, you're thinking, oh, I remember that. That's actually called an asymptote. If you approach that line, but you don't actually touch it, that's an asymptote. Okay? So as x gets really, really large, we're getting closer and closer to this line. As x goes to infinity, we see that y approaches the line. Okay? All right, so let's go ahead and figure out what that would look like then. How would we draw those asymptotes? What does it look like graphically? All right, so what we're dealing with here is on our coordinate plane, we have two kinds of graphs actually, just like ellipses. As the x value is getting larger and larger, you're approaching that line b over ax. Notice how it's plus and minus. which means you're going to have a line that is having a positive slope, and you also have a line that has a negative slope. So you create these asymptotes that basically form an x. Okay? And with those x values, how do we actually get them? Well, the slope of your line, keep in mind, is it has a rise of b and a run of a. Okay, so that's how we get to these locations. We also go down b and left a in this way, right? The negative b, negative a. And that's how you can create your asymptote. The same thing can be said for the negative slope. You go up b and to the left a, right, negative a, and you can also go down b and to the right by a as well. And so what you end up creating is almost like this rectangle formed along the asymptotes. Now that rectangle plays an important part in being able to draw our next conic shape. Our conic that we're forming is what's called a hyperbola. The hyperbola has vertex right here along that edge of the that dotted line, along that box. Okay, so this is going to be one of your vertices. So this is going to be a vertex. And then your hyperbola basically just says as x gets larger and larger, you approach but never touch those asymptotes. Okay, so now we're going the other way around, and we're going to get closer and closer but never touch those asymptotes, like that. Okay, and the same thing can be done on the other side. We also have another vertex here, and then we just wrap around, getting closer and closer to those getting closer and closer to those asymptotes, but never touching it, just like that. Okay? And you do want to make sure you draw your hyperbolas so they are getting closer to the asymptote. One thing that I should not see is well, I'll show you later. No, I'll show you now. It's a hyperbola where it's going like this. What's wrong with this? Look at this. The gap between the hyperbola and the asymptote, it's actually getting larger as it goes on. Notice how I just kind of wrap it and make it come in like that. Right? That's not what we're doing. We want to make it get closer to the asymptote. So do be aware of that. Okay? So that would be a no to that kind of hyperbola. All right. Now, just like we saw with ellipses, we have this, what I would call a horizontal hyperbola, and that's given by our equation x squared over a squared minus y squared over b squared is equal to 1. Okay, so that's going to be the equation of a horizontal hyperbola. Let's take a look at how that is different from the vertical hyperbola. So I'm going to draw my coordinate plane once again. Okay, and then now I'm going to do the same thing basically. I'm going to create a two asymptotes. Those dotted lines are going to be here and here. Okay, keep in mind this is just the parent function of the hyperbola. That's why our asymptotes are centered at the point 0, 0 there. Okay, so this would be our center. But what we do see also is that we're going to keep in mind that the asymptotes are a little bit different now. The equation, rather than b over ax, is now going to be a over bx. Okay, so I do want you to be aware of that. Excuse me. So in terms of finding our rectangular grid, we can see here that now we're going to rise by a and we're going to run by b. And then you can do the same thing down here. You can rise by a, negative a, and you can run by b, negative b. And you do that on the same on both sides. Okay. So you basically create another rectangle, just like that. Okay, so these are values of b, b, and then up here we have a and negative a. Okay. Now, with a vertical hyperbola, now our vertex is located here. Okay, so our vertex would make our hyperbola come up. Oops, that's a bad one. I kind of drew it at an angle there. There we go. Okay, you're coming closer to the asymptotes. Do the same thing on the other side. Just like that. And then down below, we'll get closer to the asymptote. And on the other side, same thing. So there is our vertical hyperbola. So notice how the equation of its asymptote is y equals a over bx. Okay, that's its asymptote. Versus in our horizontal hyperbola, our asymptote was y equals plus minus b over ax. Okay. And now in terms of the equation, because we have a vertical hyperbola, we're going to write a different formula now. Instead of x squared minus y squared, we're going to make it y squared over a squared minus x squared over b squared equals 1. Okay, so this is for a vertical hyperbola. All right, so what exactly was going on here? How do we make sure that we can keep track of the different kinds of formulas that you see here? Well, one thing that I like to think about is that the asymptote itself, think of that as a line. And so as a line, you tend to think of the m value as the slope. And how do we define slope? Well, that's change in y over change in x. Okay, so if it's change in y over change in x, in this case, what you see on the equation is that the y value has this number associated with it. So that's going to be like the b. And then the run has the x value attached to it, and so the x value attached to it is going to be the a. I don't want you to get so hung up on what b and a is. Rather, what I would like for you to instead think about is what is connected to the rise and what is connected to the run of your equation. Okay? So as we take a look at the next example, the vertical hyperbola, what you'll notice is that the y, which represents the rise, has this a value attached to it. So that's why we have the a value will be the rise, and then the x has the b value attached to the run. So the x, because x is running and y is rising, right, we have a over bx. So that's how you can form the asymptotes of your hyperbolas. Now, so that's the one thing I want you to remember, that when you look at the equations, basically the idea here is if you see x squared first and then y squared, because x squared comes first, it's like saying, hey, we have an x. We have like a horizontal hyperbola. If you have a y squared first, y squared minus x squared, then you're saying, oh, well, the y squared comes first, so it should look like a y. Well, there's what makes it the y, right? The vertical hyperbola. Well, you just have that other piece down there. But you get the idea, right? Hopefully, I want you to find these nice ways to memorizing what is the type of hyperbola you should have, okay? So if x squared comes first, you should have horizontal hyperbola. It makes an x. If you have y squared come first, then you should have a vertical hyperbola because it almost like forms a y like that. Okay? All right, so in our next video, we'll do some examples.